Welcome to the webinar about AutoCrear version 2.2. During 1 hour presentation, we'd like to give you an overview. Who is we? That's Ursima from GIA Informatik and Michael Martinek from e-laborate. He will give us an overview of the new version, and I think he will also give us a short outlook to the very new version which will come out in 3.0. At the end of the presentation, or even during the presentation, we'd like to answer your questions. Please feel free to use the question panel. So here some information about the presenters. That's me, Urs Simler, GIA Informatik. We are a reseller of e-laborate of AutoCrear, and I'm the technical guy at GIA Informatik. This is our salesperson. I think he is also in the call, but if you have any questions, here are his coordinates. And a very warm welcome to Michael Martinek, the founder of e-laborate and the founder of AutoCrear, and he will give us the technical presentation. Just a few words about GIA Informatik. We are a CAD reseller, and GIA Informatik is located in the middle of Switzerland. We are also dealing with SAP, and in the CAD environment we are working with a CAD system from PTC, and we have quite a lot of partners with different software solutions, and one of these different software solutions is e-laborate, and they have a very interesting tool for electrical clearance and creepage analysis. We have an own training center, and we're also doing some online trainings. If you have any question about that, feel free to contact us. That's all about GIA Informatik, about me. Then I will hand over to Michael. I think he will present his own slides. And yes, Michael, it's all yours. So I can see your screen, but I can't hear you right now.
Sorry, I muted my microphone. It's very sensible, this button.
Now it's better.
Okay, so thank you for the introduction. Thank you for hosting this event. And I hope everyone can see my screen. This is a picture of me. I'm Michael Martinek, founder and CEO of the company e-laborate Innovations. The company is almost 5 years old. And before that, I was working as a scientist at the university in Erlangen, researching about methods to compute clearance and creepage paths on complex 3D models. And I brought this research project into application by founding this company 5 years ago, starting with 3 people. Now we are already 6, and we have product AutoCrear on the market since 2017. Still our only product, so it's still covering our capacities of our developers. And this software I'd like to present today in a short overview. So it's addressed to everyone who has trouble with clearance and creepage and who's looking for a solution or tool to assist you with this. And first of all, I would like to say something about clearance and creepage in general, what the problem is. Then I'm tell you what AutoCrear can do for you in this topic. The most time we will spend today in this webinar is in a live demo, so I only have prepared a few slides here, and then we will switch over to make an entire workflow with small demo assembly so that you see all, or at least the basic capabilities of the software. And in the end, we will also give you some insight about future developments about the software. So the problem is actually that electric currents, they don't always go the way they are supposed to go. Sometimes spark can jump through the air, or currents can travel over the surface of insulation, and these are the well-known problems of clearance and creepage. And these clearance and creepage currents, they are bad. If they happen, then well, you have a shortage in your short circuit in your design, and this occurs when two electric networks are placed too close together. So this will most certainly destroy the equipment, and maybe as well the people who are operating on this equipment may be harmed or even killed if the voltages are high. So these clearance and creepage currents, they have to be avoided at any cost. But well, that's not so easy, because on the one hand, there would be a simple solution for this problem. Just build your electric networks as far away from each other as possible, but that's not actually your goal. You would like to design your assemblies as compact as possible, so this is a huge conflict. And in order to be sure to tell whether your design is safe or not, you need to know two things actually. First of all, you need to know the acceptable distances for your assembly. This is depending on many parameters such as voltage difference, pollution degree, insulation classes. It's also depending on the regions, depending on which market you want to sell your assemblies. You need to fulfill different industry standards. Also the altitude is a factor. So these are all known parameters from you, and there are industry standards who publish tables. At some point they have found out that for a certain voltage difference of certain pollution degree, it's safe to have this distance. So somewhere in some table you can look it up, and then you know, for example, that you need like 12 millimeters here between these two networks. This task can also be tough because there are a lot of industry standards out there for different scenarios, but it's not impossible. The thing which is almost impossible without a tool is the second thing you need. You need to know the shortest paths in your design. And therefore, you need to measure two different distances for each net pair. The clearance, which is the shortest path through the air, and the creepage is basically the shortest path on the surface of insulation. The clearance is quite clear. There's not much interpretation about this, but the clearance still has the additional aspect of this growth width parameter x. This is defined by the industry standards to jump over certain growths, for example. So the distance x is depending on the pollution degree, and if you have a growth which is smaller than x, then the creepage can jump right over it. If it's bigger, then the creepage can at least jump over the corner. So this is a parameter which is very, very complex, especially in 3D. And after measuring these distances, you know that you have, for example, 11.52 millimeters between these two net pairs. So this is the two information you combine, and then you can tell whether your design is safe or not, just by looking if the distance you have on your design is below or above the distance you need to fulfill. But the big problem is, of course, to get the exact results here. As you can see in this result here, you would never even get close to the global minimum path, considering all of the aspects of a creepage path in this case. So your path you determine manually will only be rough approximations. So you don't have a basis actually for a decision whether your design is safe. Even if you know how much you need to fulfill, you never know if you really fulfill it in your design. So this is where AutoCrear comes into play. For the first thing you have to know the minimum acceptable distances. There's really not much we can do about this. I mean, you have to know your parameters, your pollution degree in which you want to sell or use the assembly. You need to know the standards you have to fulfill. However, there is some help we can assist you in the program. So in the program you can enter or import these requirements so that you can so the program can also make this decision whether the determined paths are correct or not. Maybe in the future we can also offer the industry standard tables in the program. This is not possible because this is top secret information from the certification authorities. You know, they want to sell these tables to you, so it's not allowed to publish them in any way. So we are also not allowed to publish them in the software. Maybe in the future when we have more cooperations with the industry standards, which we already have ongoing. But the core feature, of course, of the software in the current state is the exact determination of the clearance and creepage paths. So the solution of the geometric problems, where exactly the critical paths are, and this is the information you definitely need in your product design, and the software does more than that. So this is of course the core feature, this computation engine, but we have built a complete software solution which includes all the steps you need to perform in order to make this analysis, starting from the raw data you have in your CAD system or in your ECAD system, your PCBs. You don't need to do any preparation of this data outside of the program. Any step you need to eventually get to a documented analysis result can be performed within the software, which is the import of the data and combining data from the two different worlds, mechanical and the electronical world, with a minimum effort. You can assign the material properties in the program if you don't have assigned them yet in your system. You can define your electric networks. The latter two are only required actually for mechanical designs. For electronical designs, they are already in the data and we automatically import them. Then you can define or specify your analysis parameters and eventually compute the creepage and clearance paths, investigate the results, and create a document out of the results. So every step which is possible to make automatic is done automatic in the software. So with minimum effort you can get a documented result regarding clearance and creepage. And we also implemented this in a very nice workflow which is very intuitive and easy to handle and easy to understand. And this workflow I would like to present to you now live in the software. So I already imported mechanical data. This is possible here with import assembly. Let me redo this step actually. We can import, or you can import any kind of native data, which is one of the common systems, like for example SolidWorks, NX, Creo, CATIA, or you can also import step data, common format for exchange. But it's always the safest way to make a native import. In this case, I have a Creo model of our demo assembly. Maybe you have already seen this assembly in one of our demonstration videos. It's our standard model we use for demonstration. It doesn't have any useful application. It's just a very simple connector, kind of a connector we modeled just for demonstration. And along with the geometry, we can also import the original colors, as you can see here. But it's very convenient, especially for the first steps in the algorithm, to see the material parameters, because this is the first step we need to perform in the workflow. Let me make a little more space for the 3D viewer. So the entire workflow happens here in this area. You will be guided through the entire process step by step. And the first step is the assigning of meta information, especially material information, which is information whether a part is insulating or conductive. And this is done by the CTI value, the comparative tracking index. As a value of 0 indicates conductive material, while a value bigger than 0 means insulation, while the bigger the value, the better the insulation. There are a total of 4 different insulation classes, and AutoCrear needs to know this value for further steps, and you can do this very efficiently in the program. Well, if you have such value somewhere in your data, it's no problem. We can also implement them automatically. As you can see here, this is a different color because it already has a material defined in the data, and we automatically imported this. But this is rarely the case that anyone has CTI values implement or specified in the data. But in the program we can do this very, very quickly. I can very easily select components here and tell the program to assign the selection a CTI of, let's say, 200. So they change the color indicates the material, the blue means insulation, and if I tell the program that these 2 elements are conductive, setting them conductive, they become silver. So also very convenient to activate this checkbox here. It automatically hides everything which is already assigned. So these elements are also insulating. This is insulating. Now all the rest is conductive. I can select this immediately at once by drawing a rectangle, set it conductive, and I'm already done with the material assignment, at least on a part level. There are also certain elements like this, for example, and let's concentrate on these 2 by just showing them. This might be a customer part which is not fully modeled, it's just the hull of it, not only the interface, and this is one solid body, but it's not one homogeneous material, of course. These pins and this in the back here needs to be conductive actually. It's no problem. We can switch to surface selection, select surfaces. We can also expand a surface selection to a convex region, which in most cases is exactly the effect you want to achieve. So I have to select only one representative surface of each of these extrusions. Then I expand the convex region, and I now selected everything of them, can set them to conductive, and I'm already done with specification of this inhomogeneous parts which often occur in mechanical data. So now we are actually finished already with the material assignment. We can do more here in this first step. We can also tell the program a surface type, which is very helpful to make to eliminate certain geometric degrees of freedom. For example, this spring here is modeled in a certain position, but it can be arbitrarily rotated around its axis in the real data. So performing the analysis only on this position can be dangerous because you might miss the worst case. So what would be better is to replace this spring by our geometric representation representing all possible positions. And this we can do automatically. You just have to tell the program that this is a spring. We can make this by setting the corresponding type, spring. And the same you can do for screws, which has also some rotational degrees of freedom by setting this to screw. This has yet no effect, but in the next step there will be a processing of these assemblies. But what if we also want to add further geometry to this scene? For example, I also want to add a PCB. So no problem, we can still, as long as we are in the first step, we can add more assemblies, or also we can import PCBs directly by adding a PCB. As you can see, this is still in the beta phase, not for long. This summer we plan to release it, but it already has great functionality and ready for you to test and to give us feedback what else you need for this Pcb import. The format we need for this Pcb import is ODB++. This is a common exchange format for ECAD data. It's basically the same as STEP for the MCAD world. So every common ECAD system is able to export ODB++. And this data kind of looks like this. This is not AutoCrear. This is a simple ODB++ viewer. And if you're familiar with ECAD data, this might ring a bell. So the ECAD data is organized layer by layer. It's two-dimensional data. Here, for example, we have, clicking too much around, this is, for example, the top layer of the signal, the second layer, and so on. And this information we automatically can transform to a 3D model. ODB++ files are either stored as a compressed file or as a directory. In this case, I have an ODB++ file of a demo PCB. I select this, I import this, and then you will get an import mask, which should also look kind of familiar if you came from the ECAD world. Here you have all your layers between the signal layers. There is a dielectric layer with a certain thickness. From the ODB++ data we know the total thickness, and we distribute it uniformly among all the layers. If you want to change them, you can do this. You can also select which of the layers you want to import and you want to consider in your analysis. You could also import the solder mask, solder pass, or components on the top and on the bottom. The drills probably want to consider. And about the components, they actually are 3D data, which is not in the ODB++ data. This is mechanical information, but you can establish a database in AutoCrear with these components, and if you have done so, you can select a detailed representation of these components, and we will automatically find the corresponding package name in the PCB with the element in your database. And if I import this now, then we very quickly generate a 3D model out of it, and we place the 3D elements from the component database on the correct positions on the PCB. And yeah, also the original colors from the PCB are imported, but as you can see in the material colors, you don't have to specify anything on your PCB. Everything has already a material assigned, and yeah, you can quickly go on with the next step. But first of all, you can see that the two assemblies we imported, or the PCB and the mechanical part, is not in the correct position yet. That's well, usually the case because these two data come from different worlds, and in order to combine them correctly, we also need some realignment here. It's no problem. We can select an assembly and change the positioning, either by just moving them around or with simple snapping operations. For example, we know that this point here should match with this point here on our piece, on our component of the PCB, and then it is snapped to the correct position. There's very simple methods here to realign your two different data from the two different worlds, your ECAD and your MCAD data. And you can add as many PCBs or mechanical parts as you like. You can, for example, add an additional, let me see where I have this, an additional frame here, which should already be on a nice position. And only for this we need to define the material, additional material properties. So this is insulating, this is conductive. And well, for now I'm happy with the import. So let's analyze this entire assembly for clearance in Creepage. So we now go on, we apply the meta information. Program does some pre-processing in the background. First of all, the special part types we assigned have now been processed, and we can look them in the so-called computational mesh or special display mode, which displays the geometry which we eventually use for the analysis. And here you can see what became of the spring and the screw. It's the geometric representation which covers all the possible rotations. So this is very safe for the analysis. You get the worst case results. It's a function we will also extend for further types, further kinds of tolerances and so on. Another thing which was pre-processed in this step, so note that the pen now moved on to the next tab of our workflow. We are now in the electric net tab, where we need to define electric nets. We have 4 different containers for the nets, which represent the net type: potential free. Self-explanation is self-explanatory because it's just well, electric parts which are not supplied with any electricity, but the most important type, of course, is the type of potential. And you can see here that there is already a lot of nets here in this list. We don't need the voltages for now. which comes from the ODB++ import. So these are the original networks from your ECAD system. And also note that the pins of these components are also automatically matched to the correct net on the PCB and are combined with the net. In the mechanical world, there's of course no electric information in the data, so we just placed them in the potential free list for now, but this you can now manually change. Let's concentrate on this connector only. Let's also switch back to the original geometry. So we don't know the names of your nets, but at least we could make some pre-processing by, so I can switch here the selection filter to net, then I can select the networks directly from the graphics. They are also highlighted here in this list. And you see that the nets, let's change the visibility, let's hide all the insulators so we can concentrate on, this is not what I wanted, but let's just say with this view here. So each net is, or networks are predefined by means of their geometry. That means that every conductive element, so every element with CTI 0, which is touching or intersecting other conductive elements, is automatically combined to a net. So this is already a predefined net consisting of 4 components, and this was done for the entire assembly. So I don't know, we want to concentrate on this. Now you just have to go through them, give them a name. I mean, they are here in this. Let's again switch to electric net. They are written here in the side, but there's still something to do with the nets. For example, this and this one here, they actually should belong together because they are connected through the interior of this part, which is not modeled. But it's no problem. We can just select them both, join them together or merge them together, and now they belong to one and the same net. The same we can do here with this net here. And yeah, now we can also give them a name. So this is P1. This, let's say this is a net ground. Here we have 3 networks, main A. Oh, this is not correct. Here we have main B, and this one is main C. And what else have we here? This one is R1. And now I also want these nets here, so this one to be supplied with electric potential. So I just move them over to this list of potential carrying nets. There are very much nets here because on the PCB there are kind of a lot nets, thousands of nets for a big PCBs, and this is actually not what you need for the analysis because the requirements are defined on only a handful of net groups. The net group is usually also already defined in the ECAD system and will also be directly exported to the ODB++ file, which is not the case for our PCB, but we can also import the net information for each net with certain files we support main vendors like Altium, Zuken, or Mentor. In this case, we have a REF file from Zuken, and in this file, the net groups are listed, and we automatically group together the corresponding nets. So we only have 4 groups here on this PCB, which need to fulfill distances to each other. And here we have our mechanical nets as well. Then we have our grounded net, and let's move this to this list of grounded nets. Here, what we have here, the three springs which are potential free, so we remain them in this list. And I guess these 4 remaining nets are the nets of our other frame here. Yeah, these are these 4 here. We can also combine them to a single net. Let's call this our HV net, and also move it over to the potential list. We have a 4th type, touchable. This is a hybrid type. For example, let's define this screw here as touchable. This means that it's actually potential free, so it's used in the analysis to make shortcuts through it, but it's also used as a target net, while the pure potential free nets are only used for shortcuts regarding other net pairs, but it's not appearing in any source or target list of the liquid nets. So we are finished with the network assignment, and it's very convenient, as you see, that all the networks on the PCB are already imported. This would be a really tough task to reassign them again, but you don't have to. We only have to deal with the mechanics here. And now we can go on with the next step. Well, maybe it's also worth mentioning that you can also add additional geometry which is only required for the analysis. For example, some industry standards tell you to fulfill certain distances to virtual planes, virtual surfaces. For example, some cover which would cover these 3 holes, an imaginary metal placed over this geometry which you need to fulfill some distances to the corresponding nets inside the hole. It's no problem. You can also add, for example, a surface cover here, and this will simply appear as a network in your list. You can also add a norm finger, for example, or other planes. Very convenient, because it would be not very nice if you would have to model these planes in your CAD data only for the analysis, because you would have to delete them afterwards again. So this is nice that you can keep these kinds of additional stuff you only need for the analysis inside the program. So now we are done with electric nets already, and now we can proceed with the next and the 3rd step of the workflow, which is assigning your parameters concerning the analysis. Basically, we need a matrix here. For each pair of nets, we need to know the distance you need to fulfill for clearance and for creepage. You can toggle through this matrix, so you can select a source net here, and you can select any net of type potential. And after that, you get every net. So it's also, let's hide the sample, it's also highlighted here. And after you select a source, you get all the possible target nets in this list according to this source. And here you have the corresponding value for clearance, creepage, and growth width, which you can directly assign. For example, I need 5 millimeter clearance, 6 millimeter creepage, and with 1 millimeter growth width parameter, this X, which is which denotes the jump distance for the creepage. Yeah, and you could do this for all net pairs manually, or there are more options to fill this matrix. Maybe you already have some kind of a distance matrix which looks like this, for example, where clearance and creepage path are already designed. Okay, there's always the same value. Oh, there's a 7, not a 5. But if you have such matrices which have the exact namings of the networks in your assembly, then you can also import it here. It will be automatically assigned to the corresponding pair of nets. In case of your PCB elements, there are already such files which come from the ECAD systems. For Suken, for example, it's the MTX files. For Mentor, it's special CSV files, and we can also parse them. And then we can extract the information about external and internal rules from these spacing tables and assign them either to the clearance or the creepage. This is for now basically a workaround, because actually AutoCrear was designed for pure mechanical analysis, where it is sufficient to have one value for clearance, one for creepage, and one for growth width. But now when we want to support electronical data, we need to distinguish between internal and external rules. This will be part of version 3.0 coming in summer, but in this beta version of this ECAD import, we can already do some analysis on the PCB, but only with one value. So you can say, I need, let's say, 2 millimeters between this certain net pair in order to test your assemblies for clearance and creepage. So this entire tab here will be under major revision. We will see some screenshots of this afterwards. Concerning the mechanical data, the most convenient way to fill this matrix is probably through standard tables. Standard tables are, they map a certain voltage difference to a distance value. And for creepage, they also consider the insulation class. So for each insulation class, we have different values, also depending on voltage difference. And these are the standard tables which are published by the UL, for example, or the IEC, where eventually your values to be which you need to fulfill are located, and you can input these tables in AutoCrear. That's only a one-time process, and after that you have them available here. Not here. Also, you can consider altitude corrections, and certainly we would have to make more information. We would have to specify voltages for each potential carrying nets, which is also possible, but not within the scope of this short demonstration here. So in this demonstration, we can also just use a simple value for clearance, creepage, and growth width, assign this to all of the net pairs, and then we can perform a computation. But this will take approximately 10 or 12 minutes. So in order to speed this up, I have prepared this in another session here. What's still to say about this tab here is that you can also add a tolerance. So you're probably not only interested in the values you need to fulfill, which you should type in here in this matrix, but you might also be interested in paths which are slightly above this value, and you can add this by adding a tolerance to this path. So then you will not only get the creepage values within 12 millimeters, but 13 millimeters. So I've prepared something here where individual values are located here, and also added a tolerance of 1. And after computation, which, as I said, for such an assembly would take 10 or 12 minutes, you get this kind of result. So you can also select your sources here. There's already an indication here in the source. The red one means there is at least one violation, so at least one path which is below the respective value you specified here, outgoing from this source. And if you select the source, you'll get details here. There is a list of all possible targets. And then you see the details in this 2 columns. CL stands for clearance, CR for creepage. So you can see that between main A and main B, well, we have clearance as well as creepage violations. Selecting a target will give you further details here in this list. Here are eventually located the path which we have found. And this is path in this assembly here. So if you select a path, it will be highlighted here in the 3D view, whereas we have some very nice features to identify paths which may be hidden by certain parts. For example, this path window, if I activate this, we cut a hole in the assembly so that you can see through the occluding components, and you can quickly identify the path, and then you can optimize the view. Like, for example, we need to hide this one. Okay, now we see the path very clear. We can also save this camera position for the path when we want to revisit the path again later. This was a mistake. So here we can save this camera position. Now it's saved. If I change it, I can also restore this. I can comment on each path. I can make tags, because this is now the point where you want to investigate your results. So the program already made a decision for you whether the path you found here is a safety violation or not, because you already also defined your distances you need to fulfill. But maybe for certain scenarios, this path is not a violation, so you can override this decision, tagging the path as okay. And then you can also add comments to this path, telling you why you think this path is okay. So every path here has its own log, where every tag, every comment is logged with a username. And so this is our Mr. Pearl. This is our developer of the interface from AutoCrear. He tagged the path as okay, and also the date is noted here. And by this you can investigate the result very nicely. So you can see this path here. You can say, okay, yeah, now that's a clear violation. So you confirm this as a violation. And there's another path and the back here. I'm not sure what to think about this path, so I'm marking this with this question mark. So these are the tags you can place on the path to see for yourself which path you already have visited manually. You can also comment on them, and after that you could save the session. At any time of the workflow you can save the session, and give the session maybe to another guy who will then you can open the session, and he then sees your comments, your tags, then he can change them. Well, let's for example fake this by a new user. Basically this comes from the Windows login, but we can also change it manually. So now I got the session from my colleague, Mr. Pearl, and I see, okay, what did he do? He tagged this path as okay. No, that's not correct. I'm totally different opinion. This is clearly a violation. I add my comment here, and this whole conversation is also logged for the path and also stored in the session. That's a very nice feature here to discuss about the results. We see some further results here. This, for example, is an example where the shortest path is traveling through a conductive or a potential-free element. The same should be here, and this is the case where we take a shortcut through this spring here, from this here into this net. We don't only have all the paths within our mechanical part here. We made an entire analysis of our entire scene. So we also have path from our mechanics to the networks on the PCB. For example, here we have a path to the PCB from this. We also have the path within the PCB and even in full 3D, which is very, very convenient because this cannot be done by any other tools, which might be, so let's see for which path I have here. This, for example, should be one path. Yeah, it's located here. So you see that we can also compute path within the PCB which go over different layers. This path leaves this net here, it goes through the hole, and then it enters another net here on the back. So we can make a full three-dimensional analysis of the entire scene with one tool. And after we have investigated all the results, we want to have a documentation of it. There's a nice tool which you can also customize your report, and then you can automatically generate a report like this, which is also very well structured. So we have a nice title page. We can also include your company logo. We have a nice table of content here, and in the end you also get the paths documented here for each pair of nets. And that is basically actually exactly what you need, either for yourself or also for the certification guys who want to see your critical clearance and creepage paths. And yeah, this is the big advantage of the software, that you can do this entire workflow here, and you can be sure that you don't miss any safety violations because you get the exact paths for clearance and creepage for each pair of nets. Now let me get back to my slides, as I want to give you some insights to further improvements we make in the future. So I already told you that we make a major revision of this analysis parameter setup, especially to also include all the requirements for ECAD. And in this new analysis tab, we will make a clear distinction between requirements and configurations. So you will be able to define your requirements, for example, standard tables, ECAD rules, which come from the ECAD systems where the spacing tables are, or you can define custom rules where you not only define one single value, but more values, for example, different values for different insulation classes. And then instead of typing a value, so one single value for clearance and creepage for each pair of nets, you assign the rules to the networks. And in an ECAD rule, for example, there is the additional consideration whether the path is interior or exterior, and we look at the correct value from the ECAD rule, and you can combine, for example, standard table values and your custom values for certain net pairs. So this will be a massive improvement in the next version. We will also, but this will not be in the next version, but in one of the following versions in the next years, we will also make considerations about tolerances. not only the motion tolerances but also manufacturing tolerances, which may vary in size, or mounting tolerances. And the idea is basically the same as we did for these springs here, that we change the geometry according to the worst case, the worst possible path which can happen due to tolerances. This is also a very important topic dealing with clearance in creepage, and something we will also address in the future. In the moment we have this consideration, at least for these elements such as springs or screws. And another big improvement will be made with the creepage, considering different CTI values. It's not always the best solution to get to determine the minimum distance or the path with minimum distance, because this might not be the worst case path. In this case, we have a good CTI value, a good insulation, this gray one here, where we require 5 millimeters, and we have 6 millimeters on it. So we would say it's okay. But actually, we can also create a safety violation here by not considering the shortest path, but the path with minimum resistance. And this is something we discuss in the moment with UL, so with the guys who make the rules and the industry standards. And well, the first expression from them was, yeah, that's a very good idea. They don't know if they would accept it in the final assembly, but it's very good. The program will provide this scenario so that a human being can watch over it and tell you if it's correct. So the physics about this still have to be researched from side of UL, but this is something we will definitely implement in AutoCrear, so that you always will get the worst case under the different scenarios. And in this case, we would tell that that's a fail, because we can make a percentage of compliance according to the values you need to fulfill. And this is something will also be in AutoCrear in the future. But as you have seen in this presentation already, now is AutoCrear a tool which can do you very good in your designs. So you not only can detect all the violations in your design, you see where they are, you can make target-oriented corrections in your assembly to eliminate these clearance and creepage paths, and it also helps you a lot to make your assembly more compact, because you not only see violations, but you can also see where you can maybe save more space in your assembly, because you have a lot of additional space to the requirement available. You can make your assembly more compact. So that's all for me. We are already exactly 1 hour, so I give back to Urs for the final words. Or maybe some questions came in.
Thanks a lot so far, Michael. It was very, very interesting. They were coming in some question. One question was, how long did it take to create the report you showed us? I think it was a PDF with about 60 slides. How long did it take about?
I think 1 or 2 minutes.
1 or 2 minutes.
So this was the standard design we have seen here, which is already in the program. If you want to customize it, you would need to take some time. But this is also a one-time process, so you can customize here your report, and then, or you can also use the standard layout. So if I click here on Generate Document.
Wait, you're not on. I'm showing my screen right now, I guess.
Oh, that's no problem. So I'm only showing the documentation tool.
I'll make you as a presenter again. Sorry.
So I don't know if because this is a documentation
Now we
tool
can see your
where
screen. Yeah.
we can also customize the contents of it, but you can also leave it with a default layout. And if I generate the report here, I just define the name of the PDF, and then it will take approximately 1 or 2 minutes, well, depending on the image quality, because we do a lot of screenshots. The higher the image quality, the longer it will take to make the renderings, but I think even in the worst case, you will wait 5 minutes maybe for huge assemblies with a big image quality. So this is not actually a factor to consider in your process. The entire process of this analysis, I mean, we have seen live the metadata, the electric nets, the analysis parameters can also be done very quickly with the matrices. The computation itself, 10 to 15 minutes, and then the documentation generation also 1 or 2 minutes.
Okay.
Just imagine how long would it take for you to make a manual determination of path and a manual documentation. So this will save you a lot of time.
Thanks a lot for the information. Other questions coming in about importing components from CATIA. Can we also import, let's say, material information from CATIA? I think it's about the CTI values. Or
Yes,
is it conductive or not?
So it doesn't matter from which system you import. So also CATIA is considered, and we can also import additional metadata from the user parameters you defined in CATIA. You just have to tell the program and the options what is the name of the parameter you use for CTI, and this is also future work, we can think of a material database in AutoCrear where we can map a material name to a CTI value, because it's not always intuitive to know your CTI values of your materials, but you sure know the material itself, the name of the material you use for your design. So you can establish in the future a database for materials which map them name to a CTI value, and if you have materials in your CATIA data, then you can just tell the name here. You have to do this before you make an import, whether it's valid for parts or assemblies or both. And then we automatically search for this parameter in the import, and if we found a value, then we can do something with it. In this case, we can take the material, look it up in the material database, and assign the correct CTI value for this material. Or you directly have the CTI value in your data, then you can also directly specify the name here. Anyway, we just scratched on the surface of the software here in this short webinar. If you're interested in the software, we are happy to give you an individual demonstration where we take at least 2 hours time, covering more than we could cover here in this short presentation.
Great. I think we are quite short on time. Maybe last question. There are some other questions here, but this might be the last. What about simulation, the effect of potting or conformal coating is the question. Potting, conformal coating.
Yeah, I'm familiar with these expressions, but I must say this is the expertise of my ECAD specialist, Mr. Prell, who is in charge of this ECAD interface, which is still under development, will be released in summer, as we said already. So I would refer this question to my colleague. You can send an email, for example, to Urs or me, and then I will give you the contact to the corresponding person in our development team who is in charge of this ECAD tool. Okay,
this is great. So I think because it's right now 7 minutes past 5. So I would say we are starting to, or we're finishing the webinar. As I told you, tomorrow you will get an email from GoToMeeting or from me with a download link for the presentation and also a YouTube link for the recording. If you have any additional questions technically or for other reasons, feel free to contact us. Here are our email addresses. So I would say in the end, I'd like to thank you for your time you spent right now. I hope it was interesting, the webinar, and I hope to see you soon somewhere else in additional webinars or live somewhere out in the world. So in the end, a big thank again for Michael for this excellent presentation, and I would say see you soon. Stay safe and sound, and bye-bye. Michael, what do you have to say?
Yeah, I also only have to say bye. Thanks for watching this webinar, and yeah, hope that the software is exactly what you need for your purposes, and hope to see you soon. Bye.